Madison College is here to present two projects, and I would like to ask you to silence your electronic devices. Feel free to move into the center for the next presentation, since we're kind of all a lot. That's right. So our 640 will be ready to go here in a second. I'm going to get you some lights. Stay right around.
From Madison College, spring 2014 Introduction to Engineering class. Our client is Paul Morshelzer. He's a senior diesel tech instructor at Madison College. He is also part of the Train the Trainer program, where he goes across the country teaching people about the benefits of biodiesel. Paul has collaborated with past year's engineering classes on a series of biodiesel projects. The first was in 2005. He worked with UW. They created a biodiesel reactor. This basically takes waste vegetable oil and reacts it with methanol along with the catalyst and creates biodiesel. This biodiesel has about a 6-month shelf life. So that led to his second project over here. He worked with last year's engineering class from Madison College. They designed a blending unit that's capable of blending either a B100, which is 100% biodiesel, or a B20, which is 20% biodiesel, 80% petrol diesel, and it emulsifies it with an additive in order to extend its shelf life. This led to his third and our current project. He asked us to design and fabricate a testing unit that's capable of testing both emissions and power of a diesel engine that can run on both petrol diesel and biodiesel. Paul wanted this system to be able to switch freely and cleanly between the two fuels. It had to be capable of running a variable, had to be able to run a variable load on the engine. And it also has to be highly portable because, as I stated earlier, he puts this in the back of his truck as he drives across country teaching about biodiesel. So our first problem was figuring out how to apply a load to an engine and then test the performance of that engine. What Paul currently does is he runs these tests off a dynamometer that he has in the diesel wing of Madison College. This basically, the dynamometer is hooked up to a test engine through a coupling. It then applies a load to that engine, and then it measures the power of that engine in horsepower, RPM, and torque. So there was 2 different types of dynamometers that we looked at. The first was a water brake. A water brake uses water to apply a load to an engine. It then measures that engine's ability to maintain its RPM. If we were to go this route, we would need both an engine and a dynamometer and a system to contain the water and deal with the drainage necessary to run this type of dyno. We scratched that idea. That was too much for us to deal with, so we went on to an electrical dyno, or an eddy current. This uses magnets to apply force instead of water, so we would only need to then worry about the extra power needed to run this type of dyno. But if we were going to go with a dynamometer engine combo, we have other problems to deal with. First is we would have to match the load bearing capability of the dynamometer with the power output of the engine. And then once we match that up, we would have to integrate the two systems together and then design a control unit for our operator to be able to use this system. That's a lot of problems, so we had actually, fortunately, one simple solution. When we chose to go with an electric generator, it already has the load bearing capabilities and the engine together in one unit. If you want to apply a load to the engine, you just plug something into the generator. If you want to vary that load, you plug more things into the generator. Everything's all together in one unit, and there's already a control panel integrated into the system. So once we made this decision, we were able to move on to our preliminary designs, and Gerard will tell you all about that.
So our preliminary designs, I'll show you a spill containment was integrated into the body. A lot of these, you can see any type of oil pan underneath, something like this, some type of spill containment. Should anything catastrophic happen, oil leak, something like that, we want to contain this. Another thing, if you recall from the previous slide, our engine was rated at 82 decibels at about 20 feet out, so we really wanted to try and come up with a way to contain that sound. You can see that in a couple of these pictures as well. One that we really stuck with is the one at the top right of your screen. It's low to the ground, it has spill containment, and it's nicely confined, which is something that's going to really help with the portability factor. So we had 6 main ideas that we really wanted to tackle in building this. The first of which was load concerns. Like we said, we need to vary the load on the engine. We considered a couple different ways. First off, what Machine mentioned was, what we plug into this is what's going to vary the load. So we compared heating elements to light arrays. Now, heating elements are great because they're high wattage right off the bat. However, contrary to your last 8 months in Wisconsin, you don't always want heat glaring at you. Light arrays, they have a nice visual indicator, they're on, but they also generate heat. Not as much, obviously, as something that is made to generate heating element. Both of these are low cost. Lights tended to be slightly less, what we discovered. So we went with the lights. The heating elements were bulky, difficult for the portability concern. And while the lights were fragile, replacing a light bulb is not a big concern. We went with this halogen array. Each one of these light bulbs does 500 watts. So we bought 3 of these, which lets us incrementally, in 500 watt increments, vary the load up to 3,000 watts, just about max load on our generator. They're wired individually so that eases the incremental increase. What we decided to do is remove this glass from the base and just work with what is up top here. That made it even more condensed and easier to move around. Placement was still a concern because these do still get hot and bright. We'll get to that a little bit later. The sound requirement, as I mentioned earlier, is quite loud. It's 82 decibels at 20 feet. We're shooting for something in the 60 to 75 decibel range. 82, we have this chart for comparison. Not quite to a chainsaw level, but imagine a crime baby or a water disposal, something like that. So, like I showed you with our first solution, we thought about a sound dampening enclosure. It seemed to be a little bit much, so what we wanted to do was try to pack it at the exhaust end. We found out that one of our students we were working with found out that we have a company willing to donate us a resonator body. So we're really excited about, and this resonator that is being donated us is rated at 25 to 35 decibel reduction. That, in the math, that's down to 47, 57 decibel range if it was advertised. We're very excited about this. We order it, we get it, and it's enormous. We're expecting something about 16 and a half inches in length, and we get an item that is 44 inches in length, 9 inches in diameter. We really have to start rethinking a lot of things in our production. Starting with the base build containment, this is what we do here.
Alright, as far as the basic spill containment of the unit, we were originally given designs for a 4x4 frame, so it would be highly portable. However, with the addition of our resonator, we had to reapproach our client on a 5-foot by 3-foot base design. After we approached him on that, he did approve that, and so we continued on to the spill containment aspect. The engine and oil and fuel of the engine totaled up to about 5 gallons worth. So we had to make our spill containment to contain at least 10 gallons for different sloshing around with the fluids. Our actual ended up being about 20 gallons of spill containment, which gave us plenty to spare. For the mobility aspect, we went with some steel casters onto the base. And in this photo here, you can see that we have these steel casters right down here on the base. And we went with 1 inch by 1 inch square tubing for our frame design with the spill containment around the edge. As far as the fuel considerations for our product, it had to be easily available to switch between petrol and biodiesel fuels and prevent minimal cross-contamination to provide accurate results. The solution that we came across for this was to use two separate three-way valves and short fuel lines in between the engine and our fuel tanks. This is the schematic of our fuel lines. As you can see, we use the two three-way valves very close to the engine, and we actually return the fuel lines back into the supply lines. For this case, we were able to do that due to the fact that the interior diameter of the fuel lines was small, so the turbulence in there was negligible. However, for large-scale applications, this would not work. As far as the emissions went, this was one of the main features that our client wanted us to be able to test. So we had to design a way to draw out a certain amount to use for our particulate filter as well as our combustion analyzer. We decided upon a vacuum pump route to draw out a controlled amount of the exhaust so that as the engine varies its load, we do not get different readings in exhaust through the filter. And for the combustion analyzer, we are using the Baccarat PCA2 combustion analyzer that the MATC diesel and heavy machinery department has. This will allow us to measure the various exhaust fumes, such as the sulfur dioxide of the petrodiesel. Our final calculations for budget, with the generator taking up the majority of our budget. Our original budget that the client gave us was $1,500, and we came in at about $1,400, which gave us about $100 worth of savings, and came in under budget. And for the fabrication of our project, we started with the generator there. The first steps behind that were to determine where we wanted the fuel lines and where we were going to position the fuel tanks to prevent the long fuel lines. Here we have two of our classmates working on the positioning of them as well as the brackets to hold them in place. For the welding of the base, we had to, like I said earlier, we used 1 inch by 1 inch square tubing. So we built that. Here we have a few photos of them welding and grinding the base. For the mounts for the resonator, we actually used the MATC water jet to cut out the required steel parts. And that was a very interesting process to behold. For the light array, we decided to mount them across the back of our generator, propped up over our resonator to prevent from using up too much space. As well as we also have a photo up in the upper, well, on the right side of the screen there with the three-way T back into the fuel lines for the fuel return and fuel supply. For the painting of this, we had to paint the metal because biodiesel has certain properties that can erode metal and react with metal. So we decided to paint it. The client did specify that he wanted the fuel tanks two different colors, green for the biodiesel and yellow for the petrodiesel. And for the frame, we coated that in a biodiesel resistant paint. This was the finished system that we came up with the light array across the back along with the resonator and the vacuum pump and the exhaust probe would be coming out that end. As well as we have the three-way valves on the front side to keep them as far away as possible from the hot parts of the engine. This project was made possible by generous donations from Nelson Global Products. The resonator that we received from them was about $264. And it was also made possible by multiple donations through Madison College, such as the chemistry department for the exhaust filters, the diesel and heavy machinery department for a lot of the actual engine components, such as the fuel tanks, fuel lines, and valves, and the auto collision department for the paint. And that was about $420 savings. Are there any questions at this point?
How much time did you spend?
We spent the whole semester. The first half of the semester was primarily on the design aspect of it. And right about halfway through, we ordered our generator. So we really only had about
the past couple weeks we were actually building
fabricated.